Neural network pruning explained. Reduce on-CPU prediction and model storage cost by zeroing out weights while minimally increasing the loss. So hello, happy to see you again. So there's another video. I read a couple papers on pruning on decision trees, and I would like to speed ups that you can get on CPU with after pruning. I create these kind of videos. If you like them, you can follow me on Twitter, YouTube, LinkedIn, Facebook, RSS. You can ask me a question. You can donate on the site. You can subscribe by mail as well. And there are other papers that you may like here about tokenization, embeddings, multi-model image classification. So pruning performs lossy compression of the model during repeated training steps to reduce prediction costs and model size. In decision trees, the pruning first improves, works as a regularization, so it first improves test accuracy, the generalization, until some sort of maximum, and after which this regularization decreases the test accuracy. This is called bias-variance. This is called bias-variance trade-off, because during the pruning we are reducing number of parameters, and that's what the bias-variance trade-off is about. I have a post on double descent and bias-variance trade-off, and double descent is an event in which we can observe slightly more complex behavior instead of just sort of convex shape of the test curve as a function of number of parameters. But let's go to the back to the pruning topic. In neural networks, we can also use the pruning. We can use the pruning to as a regularization as well, but we use many other regularization approaches in neural networks, which already prevent overfitting for us. And so neural networks are usually hugely over-parameterized. And since they are hugely over-parameterized, maybe you would like to reduce the over-parameterization. Maybe we would like to have actually maybe you'd like to save computation, and it turns out that this reduction of computation is easier to do on CPUs currently than on GPUs. Okay, what are the general pruning steps that we follow? The first step is that to pre-select so we start with some initial architecture, some initial network, and then we iteratively prune and repeat after, and we end with the training step. So what does it, how does this work? So we, during the pruning steps, we did effectively change the architecture, and since the architecture changed and we have still some weights remaining, we'd like to tune those weights with the new architecture for the dataset we are training on, and after which we can do another pruning. So this pruning is effectively, in decision trees, it's cutting parts of the decision tree, and in neural networks, it's setting some weights to 0. Okay, what are the decision trees? So decision trees are basically a tree of if-else statements, but those are only on the input variables, and they don't create any internal representations or embeddings. I have a post on embeddings here. Those are task-specific, very much task-specific representations, but oftentimes they contain the representations for one task can be useful for other tasks as well. But the decision trees don't have any embeddings. They just have these if-else statements that split the input variables into some packets, basically creating intervals, and thus are highly interpretable. We can easily understand what's happening. It's not such a black box. And these decision trees, because they are so simple, because they are just composed of these if-else statements, you can understand that I can just create enough if-else statements to overfit any data set, to just remember completely the data set. If I don't apply any regularization. There are various regularization methods that are used in decision trees, for example, pruning, minimal samples per leaf node, and maximum tree depth. On this picture we can see how the decision tree graph can look like. If we have depth of 5, we can see that the decision tree can be fitting some very much noisy training data, which maybe we don't want. Maybe we want to just fit the general shape, and that's what's called generalization. And yes, so there are two popular algorithms, C4.5 decision tree or card decision tree, where the card decision tree can also do regression, and it's used by scikit-learn. And in card decision trees, we can do pruning with an iterative greedy algorithms, which is called minimal cost complexity pruning, which removes in some sense best to prune subtrees with increasing sort of it increases the intensity of pruning, and it always just prunes the best to prune branch. It yeah, and as mentioned, it improves generalizations up to a point. The algorithm itself, what's interesting about it, that it uses this cost complexity, which is basically a loss. Here it's misclassification rate plus some alpha times some regularization parameter. In this case, it's number of terminal nodes in the subtree. So for example, here we have this tree. It has input variables outlook, humidity, windy, and temperature. And this sub branch is discovered that it's not, we can improve this cost complexity if we cut it to just simple one output, which is play, instead of this complex sub decision tree. And thus the algorithm would be one of the first sub branches it would cut would be this one, as we increase the alpha. And this is what it also reminds us the lossy regularization, and it also we can see that we sort of look at how the loss changes if we cut some part of the network. Decision tree and neural network are similar constructs, but they are not the same. As mentioned, the decision tree splits only on input variables and have no embeddings, while neural networks train linear transformations of the values and have embeddings. There is some equivalence in a special case. So neural networks with piecewise activation functions like ReLU are equivalent to extension of decision tree with linear manifold decision boundaries called multivariate decision trees. Sometimes this extension can be called something else. That kind of decision tree, which is then equivalent to neural network, it looks like this. We can see that instead of the decision boundaries as something being bigger or smaller, we take the linear combinations which need to be bigger and smaller. And pruning in neural networks basically involves what you would expect, the same as we have this decision tree. So we grow the decision tree and then we prune it. And that's it. In neural networks, this is more of an iterative approach generally. So we start with some initial architecture that can be pre-trained, and then we do pruning, we train a little bit, and we can prune again and tune a little bit. In some ways, this is a little bit similar to the decision tree algorithm, where we also do this recomputation after we prune one step in greedy way. Then maybe we can do we have this iterative approach in there in this manner. So And we basically produce a sparser architecture doing this. And pruning in neural networks can be split into unstructured pruning, structured pruning, and semi-structured pruning. So unstructured pruning just prunes individual weights. For example, magnitude pruning just removes the smallest weights. The structured pruning then removes the entire blocks like layers or heads in attention networks. And semi-structured pruning removes some sort of square blocks of weights that can help us to speed up the calculation. Magnitude pruning is the most obvious idea you could think of for pruning is if you just prune the smallest weights. And but however, we can also think about this more general approach of actually looking at the approximation of change in the loss for a corresponding task, and we can then cut weights that don't contribute to achieving our goal of some sort of loss optimization. So we can prune networks by estimating the loss changes. This is similar to decision trees, where we basically see we have this term, this cost complexity composed of two parts, and so here we zero out weights that don't change the loss based on the Taylor series of the approximation of the loss. We cannot actually predict very far how the loss would change. If we could do that, we wouldn't need a gradient descent. We could just optimize one step, but since this is very hard, we need to approximate, and we can approximate using Taylor series, which involve derivatives, and yeah, we can do the first order approximation based on the training loss gradient. So for example, this movement pruning removes those weights with the gradient pointing towards zero during fine-tuning on a downstream task. However, if the network is optimized for certain task, we are not retraining for some other task by fine-tuning. Instead, we already have a network trained on certain task, and then in that case, the gradient is effectively zero, right? Because the network is already optimized. So then we need to work with the second order pruning based, which is second order derivative, which is called Hessian matrix. And then we need to prune based on that. There is this MFAC method. And so there are several there are several approaches. We can use this magnitude pruning, this paper, and there's a tons of API for this magnitude pruning. There's also this low theoretic hypothesis paper, which has this hypothesis that when we randomly initialize an architecture, there's already some subnetwork that is going to perform excellently for us, because we just roll the dice and initialize the subnetwork very nicely for us. And in this paper, they produce a method that actually finds this subnetwork and then show that if you just fine-tune this subnetwork, it's going to perform actually very well. That it's that there are these winning tickets to be seen in these randomly initialized architectures already. And there is this optimal paired paper in 2022 that is described below, for which has this special approximation, that special pruning, which can be used for higher performance on commodity CPUs, which can save costs in cloud and computation, and or can be used on small weak devices on edge, for example. So this optimal BERT paper, which was published by Neural Magic company, achieves the same latency on 4-core CPU as A100 GPU with byte size 1. I haven't verified this claim, but apparently the metric accuracy metric just shows 1% difference, but 10 times a smaller model. The method effectively just extends the second order structured pruning, and it uses a Fisher information matrix approximation of the Hessian. It speeds up an inversion that is being done there, inversion formula with blockwise approximation, and then fine-tunes with knowledge distillation. So we retain this densely trained model, and then we fine-tune during the pruning the smaller pruned model, the sparse model. And even after that we can fine-tune on some other tasks, but again we need the dense model, and for the fine-tuning task, for the downstream task, to keep the accuracy good. And okay, and what's to be mentioned again, so this is something that can help us with prediction, but not the training. In fact, the training becomes more complicated while the prediction becomes faster. And this optimal BERT is can be highly optimized for execution on CPU, while on GPU it helps only. So on CPU you can optimize it for 8 times speed up, while on GPU you can optimize it only for 2 times speed up. Okay, here are results from the paper when compared to distal BERT. These are sort of distillation methods. They are not really pruning methods, and you can see that you can get the speed up. And to actually execute these sparse networks, this company Neural Magic produced a closed source inference software for sparse models optimized for CPU using multi-threading. And they publish actually also a way how to prune neural networks that's open source, but the actual execution itself, it's patented and it's closed source. And there's some pricing if you want to use it in production. And how does it actually work? So we have this, there's this image of comparison of CPU and GPU, the cores, the size of the cache, and to compare, like this GPUs is optimized for doing large matrix multiplication, so you distribute the task across many cores. Those do only a small calculation, and then you download everything back, and like basically you just redistribute again to calculate the next multiplication. On CPU you have less cores but bigger caches, so this pruning is actually more useful on CPUs because the CPU has a problem that it's not so fast to change what you will be calculating next. So ideally, if you can sparsify in such a way that you can produce these tangles, these tensor columns, which can stay on the CPU cache for a while, so the CPUs can be calculating in parallel, then they can exchange information and calculate forward again. While on GPU this kind of approach is not going to help so much, because if you are doing this large multiplication and just some parts are set to 0, this is not going to help you. It can help you a little bit if you optimize by removing some parts of the multiplication, but this is where CPU can actually shine thanks to the caches. So on their webpage they say, but once flops are reduced, the computation becomes more memory bound. That is less compute per data item, so the cost of the movement in and out of the memory becomes crucial. Rather than execute network layer after layer, we are able to execute the neural network in depth-wise stripes called tensor columns. Each tensor column stays completely in CPU large fast caches, allowing full execution length of the neural network. In this way, we almost completely avoid moving data in and out of the memory. The cost estimate. So I did a little bit of an experiment to compare this Distilbert and OptimalBert, and I can see that the Distilbert latency is bigger on my CPU, and while the OptimalBert should have also higher accuracy. And also based on the pricing in Ohio, and if we are comparing this T4G X large with G4DN X large, which has T4 GPU, the cost cut could be twice or 4 times the cost. I'm not exactly sure how much it could be, but this is the kind of savings that potentially can be gained. Again, as mentioned before, some parts of the neural magic code are open source under actually Apache 2 license, but the inference engine itself, it's a patented technology, and I don't fully understand like how these patents work, but this in particular is patent technology, and it has a restricted license, not production use, and there is some sort of pricing if you want to use it for production. Neural magic has it's led by research scientists and professor in memory and parallel computation, so that there seem to be, and also based on the paper, there seems to be definitely some kind of merit behind this solution, but I haven't investigated the pricing, the alternatives, what the patent really means, and so on. So in summary, that there may be a potential for you to save 2x money. Will be still looking at this. I'm not fully. I haven't fully tried out everything here or understood all the alternatives. I don't really know how much the deployment of potentially this inference engine from neural magic would cost, and training here still requires GPU, but maybe that's not an issue if you just have lots of predictions and very little training. Maybe that's fine, and you can still do some fine-tuning on the sparse. Yes, yeah, never mind. If you just do predictions, you could get these savings. If you need training, actually the training becomes more complicated. There's some disadvantage of using this specific solution from neural magic, that there's going to be some sort of vendor lock-in, and so maybe you would be thinking like, what could happen if you needed to switch? What would you do? And I don't see clear alternative. There is this Vertigo AI, but I'm sure there must be some others. I'm not quite know just yet. Yes, and that's and okay, and that's going to be all for me. That's like the distillation of the biggest ideas on this topic. There are other posts that I have here on tokenization, embeddings, multimodal image, image test classification, transformers, compression using neural networks, and so on. You can follow me by mail. You can get the newsletter. You can follow me on YouTube, LinkedIn, Facebook, RSS. You can donate, ask me a question, and yes. So also there are other interesting YouTube channels. For example, Yannick Kilcher's YouTube channel. There was recently interesting videos on neural magic, exactly about the execution engine. There was an interview with Nir Shavit, which is the manager of neural magic, and as well, there was recently there was this huge hype about how decision trees are similar to neural networks, which in fact is actually trivial. It was known, but there was also like interesting video on there about this. Okay, so thank you very much. I hope to see you next time, and yeah, let me know if you have questions, and yeah, enjoy your programming. I hope this is going to be useful. Bye.